Welcome. We're going to talk today on this lecture about solar electric configuration. How do we configure, what are the different configurations that you'll find for solar electric systems? First, I want to tell a little bit about the solar electric cell and how, what its history is. It was invented, believe it or not, in 1839. We tend to think of solar cells as something that's ultra high tech, but it's actually invented by this French scientist named Becquerel. And I have a friend who's a solar researcher, and he actually found Becquerel's original cells and measured the output of them, and they still would put out the whatever it was that they put out in 1839. They weren't particularly efficient solar cells at the time, but they weren't particularly efficient solar cells because we hadn't really figured out how to do that. We didn't get really efficient solar cells that could produce a lot of power until in the 40s and 50s when Bell Labs started working on them. You can see this advertisement. Bell System solar battery converts sun rays into electricity. And there was a lot of attention put on developing solar cells as a power supply for space because they needed something that was very reliable, and there's nothing that's used up or moves in the process of making electricity from solar cells. So they're very reliable and they last a long time. We've got spacecraft that have been out in space in the harsh environment of space for 40 years, and their solar cells still work just fine. And so let's take a look at how a solar cell works. Oops, that's the wrong one. Sorry about that. Let's go back and take a look at that again. Oh, again, that's the wrong one. Sorry, let me go back and see where we're having trouble with that. So here we go. So let's take a look at how a solar cell actually works, how it does that magic of converting sunlight into electricity.
Solar cells convert sunlight directly into electricity. We start with sand, which is processed into highly purified silicon. In a process called doping, trace amounts of special impurities are added to this purified silicon. For example, when silicon is doped with boron, the resultant material is called p-type. When silicon is doped with phosphorus, the resultant material is called n-type. When pure silicon is doped with both boron and phosphorus in just the right way, a p-n junction is formed. This process establishes a permanent electric field in the crystal. When a p-n junction is made so that light can strike its top surface and metal conductors are attached to the p and n-type sides, a solar cell is formed. When sunlight strikes the solar cells, electrons are ejected from the atoms, and the permanent electric field in the junction steers them to the n-type side. If a wire is connecting both sides of the solar cell, electric current can flow whenever sunlight is striking the solar cell.
Welcome back to another exciting adventure of guns, thugs, G's, and hoes. The actually are gonna
Let's go back to our presentation. So here's a solar cell, and you can see the little wires that collect the electrons when the sun's energy, when the photons from the sun, hit this silicon, this piece of silicon, very thin piece of silicon that's has a doped on one side with excess of electrons, and on another side with a with too few electrons. So one's N side negative and one's P side electrons are negative. P side absence of electrons is positive. So right at that junction, when sunlight hits that junction within this cell, then it makes electricity flow. And then the electrons are picked up by these little wires. And it's tricky because if you don't put enough wires, you won't collect all the electrons. If you put too many wires, you'll block all the sunlight. So individual solar cell, and a solar cell, every solar cell, no matter how big it is, puts out the same voltage, every individual cell. And the current that it puts out is going to be related to the size of the cell. So a bigger cell will put out more current. Let's say you have a cell that puts out 1 amp. If you have a cell that's twice as big, it'll put out 2 amps. And each solar cell puts out about a half a volt, no matter how big it is, silicon solar cells. So then a solar panel is made up of a bunch of solar cells put into a package. And let's say you want to charge batteries with this system, then the number of cells you need, the rule of thumb is roughly the battery voltage times 3. So example, if we charge a 12-volt battery, would need 12 times 3 or 36 cells. So if you take a solar panel and you add up the number of cells and it equals 36, you know that solar panel was designed to charge a 12-volt battery. And if we look at this one, it's 1, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 1, 2, 3, 4. That's 36 cells, so this is a 12-volt solar panel, and it's one of the solar panels in the system that used to power my place in Hawaii. Now, solar cells don't, they put out voltage and current in a particular relationship, and it's called a voltage current curve, and this is what it looks like. So 1,000 watts per square meter, if you remember, that's the kind of maximum. It's the solar constant. That's what we get sort of maximum from the sun at the high noon and in the desert on a clear day. That's kind of the maximum that'll hit the surface of the earth. And we put out one individual cell will put out about a half a volt, but it'll put out about half a volt, and this particular cell will put out 2 amps of current maximum. And so it follows this. So what happens is if you're sitting there and you're not drawing any current, there's no wires hooked to the solar cell that are connected in a circuit and causing current to flow, then it'll sit there and it'll put out about a half a volt. Just like if you measure the voltage on a battery when it's at rest, it'll be a certain voltage. But with a solar cell, when you start putting a load on it and working up this curve and actually starting to draw current from the thing, so let's say we're up here at 1 amp of current, the voltage will have drooped maybe to 4.8 volts or something like that, and then it'll continue to droop till we get to this what's called knee of the curve, this very sharp section where the curve makes a sharp curve makes a very sharp bend, and you notice here that the voltage will start to drop very rapidly once we get a little above 2 amps. And right here, the voltage is actually 0, and it's just a little over 2 amps of current. Remember, the power is the voltage times the current. So if we look at this point, the current is 0, and the voltage is 0.5. So the power is 0 times 0.5, and anything times 0 is 0. So there's actually no power being produced with the cell at this point. And remember I said earlier, this is a cell that's just basically an open circuit. It's just a couple of wires hanging in the air, and it's nothing connected to it, and it'll put out about half a volt for an individual cell. And then if I take and I short circuit that cell, and I put the wires together and put it in the sun, the voltage will drop to 0, but there'll be a current of a little more than 2 amps that'll flow. But the power being the voltage times the current, or 0 times a little more than 2, it's going to be 0, because anything times 0 is 0. So here there's actually no power. So where's the place on this curve where the solar cell puts out its maximum power? Well, if we were to work our way up here, it would continue to put out more and more power, because the current continues to go higher, and the voltage is just dropping a little bit till it gets to this point where all of a sudden the voltage starts dropping really quickly, and the power drops off really quickly until we get to 0 here. So it turns out that right at the knee of this curve, and I'm going to draw that. So right at the knee of this curve right here is the place at which the solar cell, and again, a solar panel is just made up of a bunch of different cells, so a solar panel would look like this, except its voltage would be higher. Then this is called the MPP, maximum power point. So this is max. Let's see if I can draw that. AX, maximum power point, because that's the point at which if the cell operates right there, it'll always put out its maximum power. Now, if you have a solar cell that's operating in a situation where there's going to be varying loads, like if it's charging a battery, when the battery's low, it's going to have a big load on it. When the battery is mostly charged, it's going to have a low load. Then it's not always going to be operating in the most efficient place for the solar cell. So there are electronic devices that will kind of adapt between the load in the solar cell, and they'll always let the solar cell operate at this point even if the load requires something different, and they'll electronically match the two. And that's called a maximum power point tracker, or MPPT. And that's a special kind of charge controller that you can get maybe 10, 15, 20% more power over the price and energy over the time of a year, with a special charge controller that tracks this point, that keeps this point. It's not the same as tracking the sun. This is something that's done sort of invisibly. This is an electronic tracking of making sure that the solar panel can always operate right here regardless of what the load is. And they were originally developed for spacecraft because they wanted to squeeze every, it's expensive to move heavy things into space, and solar panels are relatively heavy compared to electronics, so they discovered that they could put some fairly lightweight electronics and really improve the performance of the solar array. And this is what happens when it gets cloudy. So we've got light of 1,000 watts per square meter. Remember, that's the solar constant, the maximum you're ever going to get. And if you go to 600 watts, which is roughly half, then what you're going to do, you'll see that in most cases the voltage is going to stay the same, but the current's going to drop. So the current, even at low light levels, without much of a load, the voltage is still going to be about a half a volt with no load. But the current is going to be much, much less. In other words, if you have a solar panel that is operating at 1/5 the full amount it would get on a sunny day, on a cloudy day, it's going to put out its full voltage, but its current is going to be limited. So the current you get is directly related to how bright the sunlight is, and the voltage pretty much stays the same. Here's some specifications to try to make this a little more real. This is on the back of a Renesola solar panel, and this would be a fairly large panel, 300 watts. It'd be 6 feet, 5.5. Well, here it is right here. It tells how big it is, but it's like 5 feet tall and 3-4 feet wide. It's a big solar panel. It's about as big as they make them. And these are I know that Ideal Energy here in Fairfield has used Renesola. So this says that the open circuit voltage is 44.9. Now let's go back and look at this curve. So what that's saying is this point for this particular panel would be 44.9, the open circuit voltage. And then the maximum power voltage is 36.6. So what's that saying is that the knee of this curve right here, the voltage is 36.6. So it's giving you it's giving you all the points you need to actually draw this curve. And then it's telling you that the maximum power current is 8.3. And so that would be the current at this point right here would be 8.3 for this particular panel. And that the short circuit current would be 8.7, which would be this point right here. And you notice that the maximum power point current and the short circuit current over here are very close to the same. So in this case, this would be Let me see if I can draw these. V open circuit. And then you'd have V maximum power. And you'd have I maximum power. And you'd have I, or the current, short circuit. And every solar panel, most every solar panel has this written on the back of the panel so that you can know what the characteristics of that panel are. And so let's talk about some of the basic configurations. This is an old postcard showing some passive solar collectors in California. It's a little scary. But let's look at Solar Direct. So this is me a few years ago when I was building the Eco-Village project, and I had a simple aquaponics system where I had a old swimming pool liner, a very inexpensive $200 tank that would hold, several thousand gallons of water, rainwater that I collected off the roof of these greenhouses, and fill this tank up. And then I put catfish in there. Catfish are very hardy. They'll live in really tough conditions. And the catfish would make the water nutrient rich. So I would take that nutrient rich water from the catfish and water my plants on the farm at the Eco-Village with it. And then as I used the water up, it would drop. And then as it rained, it would fill it back up. And then the new clean rainwater, the fish would make that nutrient rich also. So it's a kind of aquaponics system. And what I did is, in order to move that water into the greenhouse and water my plants, I used a solar array. Here's the solar panel that went directly to a pump. And again, you can take a solar panel and put it directly to a pump or directly to a fan. And so whenever the sun was out, I would have the ability to water my plants, and usually didn't irrigate at night. And usually you want to irrigate more when the sun was more direct in the sky, more towards the middle of the day. So this would work very well. It matched the load very well. And here's a system, this is me, that I put together for the Bullock brothers up on Orcas Island. And they have a situation where the climate there is such that for a couple of months in the summer, it basically doesn't rain at all. So watering their extensive permaculture plantings is really important. And they have a big marsh and they have lots of water. But they have a hillside that goes up, 70 feet behind them that all has to be watered. So they just use these simple solar systems connected directly to some simple pumps underneath these little tiny houses that they built. And it would pump the water up the hill. And once the water was at the top of the hill, you could just use gravity to feed it down whenever you wanted. So here's a little cartoon saying, I just don't have the energy to go out at night ever since I switched from being vegan to being solar. So there are people who are breatharians who try to live just on air and sunlight. Then there are that was a system that doesn't have any batteries. It's the solar panel directly runs the device, usually either a pump or a fan. And then the next configuration I want to talk with you about is off-grid. So that's a situation where you're not connected to the power company at all. You have to generate all your own power, which means you have to be able to store energy in a battery for use at night, or for if you need to draw more power than what would be supplied by the sun at that instant. So we've talked about these kind of systems before. Typical components include solar panels, charge controller, batteries, and an inverter here. And you might have a backup generator that ties into that inverter, so that if the power is, if the solar panels aren't keeping up, then that generator can come in. And then when the generator is connected, the inverter can change itself magically from an inverter. That's why there's two arrows here. And it can, and from an inverter into a battery charger, and it can take the AC power from the generator and actually turn it to DC and push it back in the batteries and charge the batteries very quickly. And it can also run the loads in the building off the AC at the same time. So these standalone inverters that can hook hook generators up to them are quite sophisticated. But kind of ignore that for now. And the the thing to really remember is you've got solar panel, you got the sun, you've got a solar panel, you've got a charge controller which keeps the batteries from getting overcharged. You've got, coming out of the batteries, you've got you can run DC appliances directly through here, or you can go here and go to inverter, and then from here out it's just like standard house wiring, just like you were connected to the power company. And again, this one has a option for a backup generator. This is a system I installed at the Seed Center, which is next to the Eco Village. Some of your classmates live out there, Mark Chavez and some other people. And it's the Seed Center is Sustainability Education and Enterprise Development Center, and it's a place where you can go and start a farm or another business and live basically for free, because you got your electricity from solar, and you've got rain catchment water, and you've got buildings that are made of straw bale and other natural materials. And so it's an option for you during your career at MUM or after you graduate to be able to live there. Anyway, this system has batteries, as you can see here. This is the inverter here. And so then the batteries are sort of just underneath the inverter. This is the solar charge controller. And this system also has a wind turbine. We'll talk about that in a minute, how you'd hook a wind turbine up here. But a wind turbine has its own special separate controller. And so that's what you're seeing here. Then, so the DC power comes into the inverter and gets changed to AC. The AC comes out here, and you can see this is like a house circuit breaker panel. And from there on out, it's just like the kinds of things that you run at home, you could run from the utility grid, you could run from this system. Now, a hybrid system has both solar and wind. It's not just wind alone, it's not just solar alone, it's both. And so the only difference here is, you notice in this case we've got a solar panel, a charge controller, a battery bank, and an inverter. In this case, we want to add a wind turbine. We put on a different kind of controller that's special for the wind turbine and connect it to the battery bank. And the reason, we'll talk about the reason why those controllers are different when we talk about wind power, but you can see it's very simple to add a wind turbine. And you could also add a hydroelectric power turbine to this system if you wanted to, if you had flowing water that you could take advantage of. And again, here's the Seed Center, and here's the Seed Center system. We already talked about that. And then we could have a system where we were connected to the grid, and we also had batteries, so that if the grid goes down, we could then still supply energy to if the grid goes down here. We can still supply energy to our loads from the solar panel and the batteries, but we've got the grid for backup, and we've got the grid to allow us to take surplus solar energy, like when all of our batteries are full and maybe the demand for energy is low in the building, then surplus energy can flow back out to the power grid rather than just being thrown away. And put systems like this up in Alaska. There are many systems like this, but the most common system that's going in now, because it's much simpler, when you have to deal with batteries. Batteries are messy electrochemical devices, and they require maintenance. Hardly anything else in the system requires maintenance but the batteries. So can you eliminate the batteries? Well, it turns out you can, but there's one sort of can be a big disadvantage, and that is with a grid tie system without batteries. If the grid goes down, even if it's sunny, you don't have power. This system relies on the grid being there for it to work. And in effect, the grid is kind of like your battery here. So what happens in this system, again, is conceptually very simple. Generate solar electricity, DC electricity. That goes into an inverter, special kind of inverter, that plugs into your home's electrical system. And instead of drawing power, as most appliances that you plug into your electrical system do, it produces power. And instead of drawing power from the grid, it can pump power back out to the grid and spin the meter backwards. So this is one of the first grid-tied systems that was put in Fairfield. I designed it. It's over at the Maharishi School. And this is the solar panel. This is the inverter. This is a safety so that if you can disconnect the solar panel if you're working on the inverter. And this is a safety that allows you to disconnect the grid if you're working on the inverter. So it's conceptually very simple. And you can really see the whole layout here. Solar panel, inverter, disconnect on the solar panel side, and disconnect on the grid side. And this rack, very clever rack, allows you to just turn a small screw and adjust it for the season. And I didn't design this. There's a guy named Nelson LaFrancis who's a very clever metal worker in town, and he makes all of our solar panel racks and wind generator towers in town, or he did for many years. Now, there's a couple of different types. I want to talk just a little bit about how these systems are designed and they work in a little bit more detail for grid-tied systems. So grid-tied systems, they have to operate at a particular voltage. And so you need to put, remember when you put batteries or solar panels in a series string, the voltages add. So you have to put enough of these in a row to get a high enough voltage for the grid-tied inverter to work. And a lot of these operate around 300 volts. And if a solar panel is about 30 volts as it's at its maximum power point, then you'd have to put 10 of them in a string. And so the trick here is to look at the specifications of the solar panel and what voltage it operates at, and the specifications of the inverter and what voltage it operates at, and create strings, series strings of solar panels that give you the voltage you want. It can't be too much, it can't be too little, it has to be just in the right spot. And then let's say that one string of these panels, let's say it's 10 and they're 100-watt panels, a 1,000-watt string, then if you want 2,000 watts, you'd have to create another string exactly like this first one. And if you want 3,000 watts, you'd create a third string. 4,000 watts, a fourth string. And again, the inverter has to be able to handle the ultimate amount of power that's coming out of the strings of solar panels. And then those strings are all sort of brought together at one place, and then the wire run to the inverter from the solar panels, wire run to the inverter from the power company, and you're in business. So let's take a look at in a little more detail. So here's some inverter specs, and maybe you'll be able to understand these with the conversations we've had already. So this is telling you that this inverter, which is called a Sunny Boy 5000, it's made in Germany. It's the ones that we have. They're made in the U.S., but it's a German company because, again, Germany's a world leader in solar. And we have Sunny Boy inverters for the Sustainable Living Center. And it can operate at 208 volts AC, 240 volts AC, or 277 volts AC. It's got kind of three options. And you can see that the maximum DC voltage that you can have for the system is 600 volts. The nominal voltage is 310. And this maximum power point voltage range, if the voltage is between 250 and 480 for the maximum power point, it can track the maximum power point across those voltages. And it won't start until it gets up about 250 volts. It won't start to collect an energy. So let's go back and take a look at the, I think we've got here. Here's our solar panel specs. And so this one has a maximum power point voltage of 36. And this one says you want something that's between 250 and 480. So we could put 10 of these. We could put 10 of these in a string, 36, and that would give us 360 volts at the maximum power point. So that's within the range. It's between 250 and 480. So that would work. So that's one parameter. Now the other thing we have to check is, do we exceed the maximum voltage? And so what we'd want to look for there is, what's the open circuit voltage? It's 44.9. We have 10 panels. That's going to be 440 volts. It can handle 600, so 10 panel strings would work for this inverter. So that's the kind of design exercise you would go through. And actually, Sunny Boy, which is made by a company called SMA, SMA, and they have on their website a calculator that's you put in the type of solar panel that you're going to use and the characteristics of it, the open circuit voltage, the maximum power voltage, all that. And it'll do all the calculations for you. So you rarely have to do this kind of calculation by hand these days. And here's, that I mentioned earlier that solar panels actually work better in the wintertime when they're cold. They put out more energy when they're cold than when they're hot. And so that's kind of a myth. Solar thermal panels are different, but solar electric panels, that's how they work. And you notice this is also a Sunny Boy inverter. So when we were installing this, we got hit by a snowstorm. And again, here's the DC disconnect. Here's the inverter. Here's the meter. And here's the AC disconnect. Reason why there's a DC disconnect, because you can't shut the solar panel off in the daytime. So if you want to work on this and don't want to worry about getting shocked, because these voltages are quite high, 300 volts, then you disconnect it here and you're safe on that side, and you disconnect it here from the power company and you're safe on that side, and you can work on this device without being worried about getting shocked. Now there's another kind of system, off-grid system. There's two kind of basic types. The first one we talked about was we have one inverter, and then the solar panels are in strings of maybe 8, 10, 15 panels, whatever, however you design it. And then you'd have multiple strings. If you need more power, you have to put in another, let's say the string is 10 panels long, you'd have to put another string that was also exactly 10 panels long of the same type. There's another system where instead of having one inverter for a whole lot of panels, you have smaller inverters, but each solar panel has its own inverter. This is called microinverters, and we'll have one in the classroom once we go visit Ideal Energy. They're going to let us borrow one for the classroom. And so in this case, the way this works is the solar panel puts out DC. It comes down here to this inverter. This is the plus and minus DC. And then in this inverter, it's converted into utility grade power. And on this side is like a long extension cord from a circuit breaker in your house, or an outlet in your house. And so this is AC from the power company that's actually run to each panel on the roof. And then each panel has its own inverter. And the advantage with this is that you can have sort of like, if you only want to put up 8 panels, but a string inverter would require 10, you can just put up 8 panels with this. If this particular panel gets shaded in a string inverter, that's a problem because they're in series, and having one panel getting shaded is almost like putting a kink in the hose. It'll cut off the energy from that whole string of solar panels. In this case, you just lose the energy that you would have gotten from that one panel, and all the rest of the panels are just fine because they're independent. It's AC power at this point. Another thing that advantage with these systems is that since each solar panel has an inverter, and these inverters are fairly sophisticated devices, these inverters can report on whether that panel is working and how much energy it's putting out. And you get on your smartphone, you can actually get a report that tells you how every panel in your system did. So if one of them is doing poorly, you know which one it is, and you can replace that one panel. Whereas a string inverter system, something happens, it's a little harder to tell exactly what panel might be causing the problem. And most, a lot of, this is a fairly new development compared to the string inverters, and a lot of systems that are going in these days use microinverters. This is a big solar electric system that's kind of integrated in a kind of interesting way with this building. And this is in the Big Island of Hawaii, in Hawaii, in area of the Big Island called North Kona. It's the Natural Energy Lab of Hawaii. And this is a grid-tied system. These are the inverters. You notice they're pretty big because it's a big system. And this tells you how many kilowatt hours, what the voltage is, what the output was right at that particular point in time. It was the end of the day, so it was hardly putting out anything. But you can see that all the components will be the same no matter how big the system are. They're just different size. They're just bigger systems will have bigger inverters and charge controllers and all that. Now you can see PV system specifications, the operating voltage, the operating DC current, the maximum DC voltage, the maximum DC current for this system. Finally, to close our discussion about solar electric systems, I want to talk a little bit about wire sizes. And in the lab, you'll talk about, the process you might go through to pick how big the wire needs to be in the system in order to be able to handle the current you want with a minimal amount of power loss. And the way wire gauges work is in American wire gauge, the bigger the number, the smaller the wire. So a number 18, the smaller the number. Let me see what's going on here. Yeah, so an 18 or 20 gauge wire is actually smaller than a this image is not looking right. So let's look here. Let's see. So this is a little bit better. So this will show you that, for example, a 20 gauge wire would be this diameter, and a 12 gauge wire would be this one. So the smaller the number, actually, the bigger the wire. So here we start at 20 gauge. This is kind of what telephone, 24 gauge, what telephone wire is. And then 16 gauge is kind of the smallest wire you would use for an electrical, 120 volt electrical system. And then when you're looking at hooking up the wires that go from an inverter to batteries that could carry hundreds of amps of current, then you're looking at wires that are this size, and this goes down 20, 18, 16, 14, doesn't show 14 here, but 12, 8, 4, and then it goes to 0, and then it goes to double 0 and triple 0, and a 0 is often also called an aught. So 0 gauge wire is often called aught. Double 0 gauge wire is called double aught, and then you've got 4 aught wire, which would be even bigger. And then you've also got wires that are in certain sizes, but typically you go with these gauges, American wire gauges. And that's it.